Welcome to our critical design review. We are Hypertech and we're excited to show you our product Palantir. These are our talking points for today's presentation, starting with introduction. Then we're moving on to project overview. After that, we're going to talk about our technical aspects of the project, and we will finish the presentation with demos and a quick project status. I'm Diego San Román Fernandez and I'm Hypertech's project manager. Gabriel Fulapinto is our hardware engineer. Raúl Mora Contreras is our software engineer, and Jesus Cruz Gonzalez is our network and integration engineer. These are our stakeholders, Dr. Joseph Morgan as our technical advisor and Professor Matt Leonard as our sponsor. Our NASA customers are planetary scientist Mr. Lee Graham and principal investigator Dr. Michael Evans.
To start off, we have the background, problem statement, and concept of operation. The background of Palantir is related to the Gnomon, a prototype designed for the Apollo missions. The Gnomon was a gimbal rod mounted on a tripod, so that the rod was free to point vertically. When deployed on the lunar surface, it allowed for the estimation of the sizes for nearby objects and enabled a more accurate determination of rock and soil colors by comparison. Palantir will fulfill the desire from NASA of having a 21st century version of the Gnomon. Palantir is based on the need from NASA of communication navigation relay station that is capable of communicating voice and having data storage with forwarding capabilities. The separate channels need to control the communication systems between the NASA spacesuit, the mobile station, and the base station, as well as provide accurate coordinates while the station is moving. Palantir will serve as a proof of concept for NASA. The way Palantir will work is going to be tested at various NASA field locations. There it will be subjected to extreme conditions to test how durable the prototype is. Palantir will operate to transmit voice communications via UHF and wireless data. Also, in the case of an obstruction in the line of sight such as craters and boulders, Palantir will operate as a relay system for the voice channel between the XEMU and the base station. On the other hand, Palantir will always be used as a relay for wireless data transmission from the lidar and location system. Now for the project overview, we'll start off with the conceptual block diagram. The conceptual block diagram for the voice channels starts with the XEMU and the base station. Both will have an UHF radio transmitter and receiver. On the base station, we will have an omnidirectional antenna for UHF communications between the base station and the XEMU. Also, the antenna will communicate to the UHF transmitter and receiver to connect to the microphone speaker system. In the case of an obstruction in the line of sight between the XEMU and the base station, Palantir will be used as a relay station. Palantir has an UHF radio repeater built in, powered by its own battery system, for the signal from the XEMU to pass through the Gandil staff and be transmitted back to the base station.
For the data channel CBD, we have our batteries connected to our power management system. This will power multiple components in our system and other subsystems. To the right, we can see the navigation modules and intelligence device. A power line powers the intelligence device with 5 volts. Then this device powers the navigation modules and have two-way communications with it. For the flash drive, the intelligence device also powers it and has two-way communications with it. At the top, we can see the last subsystems. We will provide them 20 to 26 regulated volts to them from the batteries. To the top right, we see ether. We will provide them the same amount of voltage and to our access point. One regulated 12 volts power line for our router and one regulated 5 volts power line for our switch. Then the switch will have two-way communications with the intelligence device. This will allow data from the navigation modules to access our private network at the XEMU and base station. There will be an interface to have two-way communications in our private network and send data over 802.11 in the XEMU. Another interface at the base station, another one at the for lost subsystem, and one for ether. There will be 2 extra power lines that are not going to be connected and are going to be used in the future.
Now for the functional requirements and performance specifications, we're going to be describing this simultaneously. Now we have different categories for this, which are going to be divided on whether they belong to the voice channel or to belong to the data channel or they belong to both. Now the first requirement that we have is power. Now we need to provide power to a set of systems and subsystems. For example, we have to provide power to all our sensors and our intelligence device and our network components, and then we also have to provide power to other systems such as other capstone teams. And for this purpose, we also need to control what power lines are active to protect the batteries. These batteries are expected to operate at 24 volts nominal, although they operate in a range that we need to regulate. Now for data storage capacity, we have the requirement to store data that we gather from our sensors. Now this means that we need to gather data continuously for 8 hours before reaching maximum capacity and requiring to override some existing data or backing up the current data storage device. For data transmission range, there are two distances that we need to account for. Now we need to account for the distance between the mobile platform and the base station, which is a maximum range of 100 meters based on the components that we're using. And then there's a range between the astronaut and the base station. Now, because the mobile platform is acting as a relay between the astronaut and the base station, this range will be double, which means the distance will be 200 meters. For the data transmission rate, we're simply required to transmit data from the astronaut to the base station and from the other subsystems at the mobile platform to the base station. For this reason, we are only required to transmit that data at a speed of 30 megabits per second. For sensing, we are required to implement two different sensors in our design. The first one would be an IMU which has 9 degrees of freedom, so it is going to gather some accelerometer, gyroscope, and magnetometer data for us, and then we're going to use that for navigation. So we're also implementing a GPS for validating the navigation data that we interpret from our IMU. Now, moving on to the voice channel requirements, we simply have that one of signal strengths, which means that we have to provide appropriate signals. We're simply going to use some off-the-shelf UHF DMR radios, and also a repeater to relay that signals whenever they're interrupted. And also, we are going to be implementing an omnidirectional antenna for communications at the base station. Moving on to our functional block diagrams, let's start with the functional block diagram for our voice channel. Now we know that operates in two different operating modes. First will be the line of sight mode. This happens when there's a direct line of communication between the high tether radio at the astronaut and then there's another high tether radio at the base station. Now this high tether radio is going to include a microphone and a speaker to enable an operator to communicate easily with the astronaut. And at the base station, there's also a physical connection between the radio and an omnidirectional antenna to facilitate communication inside the capsule. Secondly, we have the relay operation mode of the voice channel of communications. This happens when there's an obstruction or interruption between the radio of the base station and the astronaut. So we have a repeater that's going to be located at the mobile platform, and it is going to be pretty much relaying the communications between these. It is worthy of note that all of these radios will have a battery, and the batteries are built to last for longer that the mission is going to last. So no power is provided to either radio in our system for the voice channel.
In our FBD4 data channel, we receive a range of 20 to 26 volts from our batteries. This will be the input to our power management system. There will be 4 20 to 26 unregulated output power lines. 2 go to last and after subsystems, 1 for our access point with a PoE adapter and 1 for future use. Moreover, there will be 3 regulated 5 volts output, 1 not connected for future component use, 1 to power our switch, and 1 for our intelligence board. There will be also 3.3 volts regulated power line for future component use. Our single board computer will power the navigation modules and communicate with the GPS and flash memory via serial communication and with the IMU via USB. All our networking components will transmit data over Ethernet. Finally, data will be transmitted wirelessly over 802.11 from our access point to the XMU base station and the other subsystems interface. Here we can see all the voltage regulators with their power monitors. This is the basic layout of our PCB for power management. We have a reverse voltage protection from the batteries, all the outputs from the regulators going into the power monitors that have all the address line configurations and the output peripherals to our system and other subsystems. We will power our intelligence device with 5 volts from the PCB. We will have a quick hat on top of our intelligence device to communicate over I2C with the GPS and power monitors on the I2C channel of the Raspberry Pi. We will communicate over the 2 USB ports on the intelligence device with the flash memory and IMU module. Technical presentation. Electronic design. We will receive 20 to 26 volts from the batteries drawing 15 amps of current. Then we have a MOSFET connected to a Zener diode as the reverse voltage protection system. This input voltage will then go into the input of 5 voltage regulators, where 3 5 volts, 1 12 volts, 1 3.3 volts power lines will go to output peripherals and will be constantly monitored by 6 power monitors that will sense voltage levels and current, including the raw power from the battery. These monitors will communicate over I2C with a header that is connected to our intelligence device as well. Finally, for our unregulated 20 to 26 volts from the battery outputs, we have a low side switch system that will disconnect ground if necessary to protect the system receiving power from our battery.
Alright, now let's talk about our software design. Our software is going to consist about a main program. Our main program shown on the left is going to start the operating system, then it's going to start UDP client configuration, and then it's going to call the first subroutine. The first subroutine is meant to check for an existing file where we're going to store all the data that we gather from our sensors, and then some basic logic is applied so that if the file is not existent, we're going to create a new one, and if it does exist, we're just going to continue without modifying the file. Afterwards, we're going to initialize some basic arrays, which are going to store data that we gather from our sensors. Now we have two different subroutines for each sensors to gather data from them. First, we're going to have the one for the AMU, will be shown in the second to the rightmost. It's going to start by establishing connection with the AMU, then it's going to configure the device, and then we extract the 9 degrees of freedom data from it, which would be accelerometer, gyroscope, and magnetometer. For the GPS module, the procedure is the same. We proceed and establish communication with the device, then we configure it, and then instead just gather latitude, longitude, altitude data, as well as time data, just to keep track of the location and the time the location was taken. And for both the IMU and the GPS, the data is recorded into the arrays that we initialized before. And now those arrays are organized, and two things are done with them. First, we're going to store them into the file that we checked for previously, and then we're going to go ahead and upload them to our site. That site is going to be accessible by all devices connected to the network. It is also worthy of note that whenever our file creator is causing the flash storage device to reach maximum capacity, it is going to start being overwritten, but not before alerting the users through our site that the file has reached maximum capacity on the flash storage device, and it is going to be overwritten now.
For our mechanical design, I first have to mention that what is shown in this slide was done collaborating with other two capstone teams, Ether and Loss Solution. This figure contains where each component of each capstone team is going to be located at the Gandalf staff. The only component that we, Hypertech, do not plan on having in the shared Ether and Hypertech enclosure is our access point, as shown in this slide.
Now let's proceed with our demonstration. Okay, so let's go ahead and give a quick overview of what our CR demonstration is going to look like. Here, first of all, it's going to be a mobile platform. This is obviously a pretty rough representation of what the final hardware is going to be like, mostly because we're sharing the platform itself with our capstone teams. So this is just a tripod that we acquired just to represent what it's going to look like. But yeah, as far as testing for the demonstration, we're going to demonstrate a voice channel, which is facilitated with these two radios, and then we're going to test the communication between them, and then in case of obstruction, we're going to test that communication is related to a repeater here mounted on the platform. And then as far as the network components go, we're going to test the network connection. Here are the network components, including the access point to facilitate that communication between teams. You can see that the components right now are connected to a wall outlet. That is because we have not received our PCB yet, so we have to demonstrate how the components work by connecting them to power outlet. As far as the controls go, we have a Raspberry Pi here at the top of the platform. You can see that it's plugged into an LCD screen. The screen is just to show how we're receiving data from sensors and also controlling our components. We have a requirement to gather data from an IMU and a GPS. We have not received our IMU yet, so we're demonstrating how we gather data from this GPS. It's going to be pretty straightforward. We're going to display it into the command terminal for Raspberry Pi. Yeah, that's pretty much it for our overview for demonstration. Now we're going to proceed to talk about how the radios are going to be tested. Okay, so now we go on to testing our voice channel of communications. Because it has two different operating modes, we're going to be doing two different testing procedures. First will be for the LOS or line of sight mode. And for this, I will be located at radio 1 and I have another operator located at radio 2. It looks like I would be on the top of radio tower, but that is not the case. I will be instead on a terrace that's right behind it. And finally, the procedure consisted of communicating with each other by using the two radios. Okay, so right now we're outdoors because we're testing the voice channel of communication, and the way that it's going to work is we're going to have two of these radios. These are the Hypertech UHF frequency digital radios. We're going to be using two of these. One of these is going to be going on the astronaut side, and the other one is going to be going to the base station side. And like we mentioned before, the voice of communication is going to have two operating modes. One is going to be LOS or line of sight. This means that it's going to be in this operating mode when there's a direct line of communication between one radio and the other. And the way that these radios work is it has two knobs. One is going to be for volume. If I were to turn it all the way down, it's going to power it off or on. And then there's another one for channel. Right now I'm going to be on channel 1 to communicate with the other radio. So yeah, I have the other radio down here. If you can look at it, it's all the way down there in another person. And yeah, right now we can go ahead and test it out. Test. Can you hear me?
Yes, I can hear you.
Okay, so yeah, that's it. The communication is direct. There's no other device involved in the communication because if I can see the radio, that means that I should be able to communicate with it. Now, for the second test procedure of the voice channel of communication, we have the repeater test setup. This is done by using the repeater to relay the communications between the radio 1 and radio 2 when there is an obstruction. Now, to test this out, I had the second operator move behind rotor tower, which would make the entire tower an obstruction between the two radios, which means that the communication would have to go through the repeater to be relayed successfully. So in the test, we're going to communicate and make sure that our voices are heard through both radios. Okay, so now the radios don't communicate with each other, which means that we can try our other operation method, which will be with using this device, which is the Hypertech radio repeater. The way that it works is that when it is turned on, it is automatically going to relay the communication between one radio and the other. This means that it does that automatically. We don't have to set it up or anything. Just when it detects that the radios are not communicating anymore, it's going to step in and relay that information. So as you can see under the video, I'm going to try and contact her. Test.
See?
Can you hear me?
Yes.
Okay, so yeah, as you can see, the repeater is enabling communication whenever we speak. So it's pretty much not doubling the range, but instead allowing us to overcome obstructions between the line of sight of the two radios. So that was it for voice channel. We were able to determine that the radios are working correctly according to our specifications. Now going back to the mobile platform, we're going to test how the network that we're developing is going to work. Obviously, in a mission, there's not going to be an internet connection, so the way that we're going to test that our LAN is hooked up properly and that data can be transferred between devices that are in the system. We're going to test with my own computer that I will be able to connect to the LAN that we have working here, and then transfer data to and from my Raspberry Pi. So I'm going to ping from my computer the IP address of the Raspberry Pi and vice versa. That way we can ensure that we're transferring data between the devices and that the communication is possible. Here is a short diagram of how the network components are connected together. First, we have the router, which is our biggest component. It would be connected directly through 802.3, which just means it's connected through an Ethernet cable to a switch. The switch is also connected to the Raspberry Pi and the access point directly through Ethernet cables. Once this diagram is connected successfully into our mobile platform, we're able to connect a PC through wireless, which would be 802.11n protocol, which is a protocol that the access point operates at. This means that not only one PC will be connected to it. I'm just testing it out with one PC, which is mine, but in the future, any other number of devices will be able to connect to the access point. Also here is a picture of how these components look like while mounted on the mobile platform. Okay, so first, very quickly, gathering the IP address of my Raspberry Pi. You can see it right here, and we're going to be using that to ping from our PC. Okay, so the next step would be to connect my PC to the LAN enabled by the mobile platform. So I would go ahead and connect to it. For testing purposes, I have it named as Raul's Wi-Fi. That would be my name. That's what I named it when I created it. So it is connecting. Okay, once it is connected, now I am able to go ahead and try to see if I can communicate to the Raspberry Pi, because now they're in the same network. Remember, the Raspberry Pi is connected to this switch that is connecting all the network components. So if I went and pinged the IP address from my computer of the ping of the Raspberry Pi, I should be getting replies from it. Yeah, fair enough. I do get replies, which means that they're connected, they're in the same network, and I am able to transfer communications between them. Okay, so as you can see right now, I am outdoors because I'm going to test the GPS module. Unfortunately, the GPS cannot be tested indoors because when it is indoors, it takes way too long to get a fix with the satellites. So we figure it's going to be more reliable by using it and testing it outdoors. For the proof of concept of just validating the IMU data, we think this is just fine. So yeah, we created some code onto the Raspberry Pi to pull some data continuously from the GPS and display that in the command prompt, although in the future we're going to display that in the GUI, as you're going to see soon. But yeah, the way that the GPS is connected to the Raspberry Pi is through I2C. Right now this is the only device connected through I2C, although in the future we're planning to connect our PCB, which is going to have power monitors, to the I2C as well, so that we can monitor the power status on the battery and also control the different power lines that we have, so that the batteries don't dry out too much. So yeah, right now I'm going to go ahead and run that code for the GPS so that you can have a look at how it looks like. Go ahead and change the directory. Okay, so right now I have changed the directory to be located to where my Python code is located at. And I'm going to go ahead and run it. And you can see right off the bat, it is getting a fix right away. So it's showing me data pretty quick just as soon as I ran it. This was because I had the Raspberry Pi outdoors for a while, so that I had enough time to get a fix. However, once you get a fix, as soon as you run it, you're going to display that in the command terminal. Whenever the GPS is gathering data, this blue LED is going to go off. And yeah, you can see that the values for latitude and longitude are pretty accurate to where I am in College Station. Altitude will be bound to change. It's not really constant as I am in a building right now, but it should be also fairly accurate. And the number of satellites is just something I have in there for reference for checking how many satellites are going to be in contact with the GPS, just for testing purposes. But yeah, here I'm going to show you a closer look at what that looks like. At times, a data point might be skipped. That depends purely on the conditions around the GPS at every given second. Maybe it loses signal for a second, but it comes right back to give a reliable data right away. So it's something that is going to be displayed in a GUI, as we mentioned before.
This will be a short demo on the advancements regarding the user interface and team integrations. This website will be shown in the tablet integrated in the system and operated by Team Lost. The way the website will work is that we have a start and a stop button that will allow the website to grab information from the server we created to send data from our sensors in the form of JSON. Then the user will be able to use the start button and see how the status of the application has started, as you can see here. And the start button will disappear in order to avoid the user double clicking the button and running the program twice. After a short delay, the values will display and the user can keep running the program with a 5-second refresh or stop the application. As soon as the stop button is pressed, the start button will appear again in order for the user to use the status again.
For the project status aspect of our presentation, I'm going to talk about schedule, the Gantt chart. I'm also gonna show our labor and financial status, and also the major task remaining. As mentioned in the previous slide, I'm gonna talk about schedule. This is our schedule. The red line represents where we're on the project, and as we can see, the red line is right on the CDR. Next is our Gantt chart. This is a useful tool because it helps you assess how long a project should take, determine the resources needed, and plan the order in which a task should be completed. This slide shows our research phase being completed and also shows our active and soon to come tasks of our design phase. This slide shows our implementation phase and its active tasks. Here's our testing phase. Finally, our documentation phase. This is the labor and financial status section. Our labor status contains the predicted and actual hours each team member worked during the week. Also, below the table, we have our original labor estimate, which was 1,522. The current labor estimate indicates the total amount of hours we as a team have worked. Therefore, we have 462 hours left and 8 weeks remaining, so we have to work approximately 58 hours as a team this week, as it is indicated in the table above it. For our financial status, the table has all the components we have purchased so far, and it also contains the totals, the total budget assigned, the amount spent up to date, the actual amount spent without customer provided materials, the amount of this PO, of the last PO, estimated amount to spend in the future, and performance to budget. In our major task remaining section, we chose those dates since the beginning of the semester and we haven't changed them. Right now we are in our CDR. The next things to come are the beta code and the beta hardware, and we're working on them. Next is going to be the final presentation.
Overall, Hypertech will deliver a NAVCOM system with hardware, networking, and voice communication systems integrated. A reliable network that may be expanded in the future if necessary. We want to especially thank our technical advisor, Dr. Morgan, and sponsor, Professor Leonard. We'd also like to thank our NASA customers, Mr. Lee Graham and Dr. Michael Evans. And finally, we would like to thank Mr. Jim Hop.